So in this lecture, I will present the lower bound of the large deviations principle. So let me remind you of the setup. We have a measure space, omega, and a sigma algebra F. And we have defined in this measure space a probability measure. And we have in this space a family, x1, x2, of ID random variables. So I will assume that for all lambda in R, the exponential moment associated to lambda, so exponential lambda x1, that this is finite for all lambda. And I will be calling M the expectation of the random variable x1. So we introduced M a function, which is, we proved it to be convex, which is M of lambda, which is the log of the expectation of the exponential lambda x1. We proved that M of lambda is convex, and the derivative of M lambda, its derivative of this expression, we have seen it's equal to expectation of x1 lambda x1 divided by the expectation of exponential lambda x1. And so this is one assumption, and we impose a second assumption, which, as I comment, is not necessary, but I will assume just to simplify the exposition, is that the limit as lambda goes to infinity, you see that since M it's strictly convex, M prime it's strictly increasing. So I'll be assuming that the limit of M prime of lambda as lambda tends to plus infinity, it's equal to plus infinity, and that the limit as lambda goes to minus infinity of M prime of lambda, it's equal to minus infinity. And as an exercise, I proposed to assume that x1 it's an exponential with mean 0 and variance 1, and to prove that indeed these assumptions is satisfied. So the law of large numbers tells us that x1 plus xn divided by n converge to M. In probability, we proved that in the last lecture. Now we want to state the lower bound of the large deviation principle. So here is the main theorem of this lecture. We want to prove that for all G open, so a subset G of R which is open, we have that the limit imp as n tends to infinity of 1 over n, the logarithm that the average, so remember this is represented by xn bar, the average of the first n variables, so that the probability that xn bar belongs to G, so that this is bounded below by minus the infimum for alpha in G of I of alpha, where I of alpha, it's the convex conjugate of M, so I of alpha, which is called the large deviation rate function, it's given by the supremum over all lambda in R of lambda alpha minus M of lambda. So this is, well, the result which I would like to present in this lecture. So the first step in the proof will be to construct a family of measures mu lambda on the space R infinity times the Borel B infinity. So R infinity is just the product of R with R a countable number of times. So this is the space of all sequence of real valued numbers, and B infinity is the sigma algebra generated by the cylinder functions. This you certainly have seen in measure theory. So fix lambda in R. Remember that we have a measure omega, a probability space omega f, and a measure p. And on this probability space, we assumed that we have a sequence of IID random variable x1, x2, and so on. So these are IID. So with this probability space and this sequence of random variables, we will construct these measures. For that, let me fix n larger than 1, fixed integer, and I will define the measure mu n lambda, which is a measure defined on the space Rn and with the Borel sigma algebra of Rn. So remember the Borel sigma algebra, it's the smallest sigma algebra which contains all open sets of Rn. And so let me define this measure on this space. So let me take a set in Bn, and let me define mu n of lambda of A. So this is the probability, actually the expectation. So this expectation is respect to this probability of the indicator that the vector x1, xn belongs to A. And here I'll place the exponential of lambda, the sum from 1 up to n. And let me put lambda inside, of lambda xj minus m of lambda. So just observe that, just remember that m of lambda, it's the logarithm of the expectation of lambda x1, which means that the exponential of m of lambda, it's the expectation of lambda x1. And in particular, if you take A to be Rn, so this will be 1, what you have is the expectation of this exponential. Since the random variable are independent, this becomes a product, and the expectation of lambda x1 minus mn by this identity is just equal to 1. So indeed, the total mass of the measure mu n lambda, it's equal to 1. And I leave it to you as an exercise to show that mu n, it's indeed a probability on this space. So by this formula, I have defined these measures. And now I claim that this family, so we have a family of measures, and what I claim is that this family of measure, it's compatible in the sense that if I take n strictly smaller than m, and if I consider the measure mu m lambda, which is defined in Rm, but I take a set A which is n-dimensional, so let me take A, an element of Bn. So A, it's a subset of Rn, which belongs to the Borel sigma field Bn. And let me define A, I don't know, A tilde to be A times Rm minus n. So this set here, it's clearly an element of Bn. And what I claim is that if I take the measure of A tilde with respect to mu m, this is equal to mu n lambda of A. Well, this is to say that if I define lambda pi mn as the projection from Rm to Rn, so the map which sends the point x1, xm to the point x1, xn, what this identity is telling me is that if I take mu m lambda and I compose that with the inverse m n minus 1, so mind pi mn, it's sending rm to rn, so if I take the inverse image of a set, I'll have a set on Rm. Now I compute the measure with respect to mu lambda m of this set. What I get is that this is correspond exactly to mu n lambda. So I leave it to you to check that this identity holds, which it's equivalent to show that this identity holds for all sets A in Bn. And we know by Kolmogorov Theorem that if we have such a sequence of probability measures which is compatible in this sense, then there exists a measure which is defined on R infinity B infinity, which I will be representing it by mu lambda, such that mu lambda, so if you restrict this measure to the set Rn, it corresponds exactly to mu n. So formally, if I have now, I define now pi of n from R infinity to Rn, which associated to a sequence x1, x2, its first n coordinates, then what Kolmogorov Theorem tells us that there exists this measure, and with the property that if I compose it with pi n minus 1, this is exactly equal to mu lambda n. So so this is the measure which we will be working with. So I just used Kolmogorov Theorem to guarantee the existence of a measure on that space which has this property. So that if you look the first n coordinates, then this measure coincides with the measure mu lambda n, and I have an explicit formula for this measure, which relates the measure mu lambda n with the measure p through this formula. So we define this measure with, and this measure has these two properties. So now I want to extract some information of this measure. So I will define the random variables zj on this space. So zj will be equal, so this is a function from this space R infinity to R. So it's a random variable, and if you take a sequence x1, x2, and so on, it gives me just the value of the jth coordinate. And what I claim is that this sequence, z1, z2, and so on, it's an IID sequence, and that the distribution of z1 is equal to the distribution of x1, where x is the random sequence of random variables which was defined at the beginning on the space omega f. So let's prove that indeed this sequence is a sequence of IID. So let me compute the expectation with respect to the measure mu of lambda of a product from 1 to n of fj xj. So if I want to prove that this family, the sequence is independent, I have to prove that for any fixed n, x1, xn, it's independent, and to prove that x1, xn is independent, what I have to show is that this is equal to j equal to 1 from n of the expectation with respect to mu lambda of f j xj. So this is the identity which I want to prove. So let me start with the left-hand side. And you see that this function depends only on the first n variables. So I can use this identity to say that this is equal to the expectation with respect to the measure mu lambda n of j equal to 1 up to n of fj xj. Now I can use the definition of mu lambda n to rewrite this expectation as the expectation with respect to the probability measure p of, and here of course I wrote x, but I meant z. So these are the projections. Now here I can use this definition to write this product as the product from 1 up to n of fj xj, and I have the exponential k from 1 up to n of lambda xk minus m lambda. I can rewrite this expectation as the expectation of the product from 1 up to n of fj xj, the exponential lambda xj minus m of lambda. So I'm just rewriting this expression another way. Now I can use the fact that the random variables xj are independent to say that the expectation of this product is equal to the product of the expectations. Now, if I look back at the definition of mu and lambda, this is also equal to the expectation with respect to m lambda n of fj zj. And finally, I can use the first property of mu lambda to remove n, and this is exactly what I wanted to prove. So we've seen that under the measure mu lambda, the coordinates are independent random variables. Now I claim that they are also identically distributed, and in order to prove that they are identically distributed, what I need to show is that, well, the expectation with respect to mu lambda of f zj, it's equal to the expectation with respect to mu lambda of f z1. And the same computation we did in order to show that they are independent also proves that they are identically distributed. So this shows not only that these random variables are IID, but furthermore, we have also a formula for, so what I claim is that Zj has, so they are IID, but we have a formula for the expectation with respect to mu lambda. This corresponds to the expectation with respect to p due to that formula of f x1 exponential lambda x1 minus m of lambda. Okay, so we have, we know how to compute the expectation of any function of z1 with respect to mu lambda through this formula. In particular, what I claim is that under this measure mu of lambda, z1, the expectation of z1 will be equal to m prime of lambda. And so let me show you that this identity holds. So by definition, I can put here mu lambda 1. So this is equal, because we have this first property, that mu lambda 1 of f z1. Now, by definition of mu lambda 1, this is equal to the expectation, now with respect to p of f, and here it's z1, sure. This is the expectation with respect to x1 of exponential lambda x1 minus m lambda. But if you recall the definition of m lambda, I can rewrite this as the expectation of x1 exponential lambda x1 divided by the expectation of the exponential lambda x1. And this is exactly the formula we have for the derivative of m computed at lambda. So we have indeed this identity. So we proved that under this measure, the sequence z1, z2, which gives the coordinates, so the coordinates are IID random variable, and they have mean given by m prime of lambda. And based on these measures, we will prove that the lower bound, let me just take from this fact and the fact that the sequence is IID, that under mu lambda, what we have is that z1 plus zn divided by n converge in probability to m prime of lambda, which is saying that under the measure mu lambda, for all epsilon positive, z1 plus zn divided by n minus m prime of lambda larger than epsilon, that this is going to 0. So this is, we have the proof I presented in the previous lecture show that indeed this statement holds, because, well, we can just use Chebyshev inequality and the fact that all these variables have an exponential moment under the measure mu lambda. So we will use these informations in order to prove the lower bound for the large deviations. So this is the statement we want to prove, and for all G open set. So fix G open, and let me fix an alpha in G. So since G is open, this means that there exists a delta positive such that the ball which is centered at alpha, and let's say that this is delta 0, that this ball is contained in G for all delta smaller or equal than delta 0. Since G is open, we can find a radius delta 0 such that this ball is contained in G for all delta less than delta 0. And therefore, I can bound the probability that xn bar belongs to G by the probability that xn bar belongs to the ball of radius alpha, of radius delta. So I fix a delta smaller than delta 0, and I can bound, therefore, this probability by that one. Now, we have seen that this probability corresponds exactly to the probability mu of 0 Zn bar belonging to the ball of alpha delta. Right? Because, of course, we have a connection of mu lambda with these probabilities with exponential lambda, but if you take lambda equal to 0, what you get is that from our previous definition, is that mu 0 of x1, xn in some set A, that this is exactly the probability, and this is z in my notation, that the probability that x1, xn belongs to A. So I leave it to you to check this identity so that I can rewrite in terms of mu 0 all probabilities referring to P. So this is what I did. I replaced P by mu 0, and now I'll just rewrite this as the expectation of mu 0 that Zn bar belongs to this ball of radius delta and centered at alpha, and I will introduce n. It's fixed, so let me rewrite this as the sum of lambda from 1 to m, lambda xj minus m of lambda, exponential. So I just multiply by this exponential. Now I'll divide by the same exponential. So I didn't do much, and I'm always replacing z by x. So I multiplied this probability by this exponential, I divided by the same exponential, so I didn't do much. And here I'm free to choose lambda. So we'll see that there is a precise choice of lambda, and that we will use in a second. Now, what I wanted to claim here is that, let me look at this expression. This expression, what do we have here? I can rewrite that as lambda times n times z n bar, right? This first sum. And let me write everything. So this is n times lambda without the minus sign, right? Minus m of lambda. So this corresponds to the sum, and if I want to include the minus sign, let me place the minus sign here. Fine. Now I know that Zn bar belongs to alpha delta. This means that Zn bar, it's less or equal than alpha plus delta. And since I have a minus sign here, this tells me that this is larger or equal than minus n lambda alpha plus delta minus m lambda. So, well, this is a number. It doesn't depend anymore on the random variables, which means that I can bound this expression by exponential minus n lambda alpha plus delta minus m of lambda times the expectation with respect to mu 0 of the indicator that Z n bar belongs to the ball centered at alpha and with radius delta, and then the exponential of the sum of lambda Zj minus m of lambda. So here we just use the fact that Zn bar belongs to this ball in order to get this lower bound. Now, what I claim is that this expectation corresponds to the expectation E lambda. So I leave it to you to check that this corresponds to the expectation with respect to the measure mu lambda of the indicator that Zn bar belongs to the ball of center alpha and radius delta, and we still keep the exponential minus n times lambda alpha plus delta minus ml. So I need to check that indeed, if I take the expectation with respect to mu 0 and I add this exponential, what I'm actually doing is that I'm taking expectation with respect to mu lambda. This is a simple computation which relies on the definition of mu lambda, which I gave a few minutes ago. Then, well, this is very nice because now I claim that if I choose lambda correctly, this will converge to 1. And why is that so? Well, because I know that under this measure, these random variables are IID, and they have mean equal to m prime lambda. So if I choose lambda in such a way that m prime of lambda is equal to alpha, I know that this sequence is a sequence of IID random variable with mean lambda, and therefore that the probability that Zn bar will converge in probability to alpha. So I can rewrite first this object as mu lambda that Zn bar belongs to this ball, but Zn bar belongs to this ball means that Zn bar minus alpha is smaller than delta. And then I still have the exponential minus n of lambda alpha plus delta minus m of lambda. But as I said, if now I choose lambda in such a way that m prime of lambda is equal to alpha, then this means that under this measure, these are ID random variable which mean alpha. This means that whatever delta, strictly positive, this will converge to 1. And this is where I use the assumption that mu prime lambda converges to plus infinity when lambda goes to plus infinity, and to minus infinity when lambda goes to minus infinity. I know, since m is strictly convex, that with that assumption there exists a unique lambda which has this property. And what is this lambda? This lambda is equal to m prime, the inverse of this function, computed at alpha. So let me choose lambda by this formula. In this case, this expression converges to 1. So up to now, what I proved, if you summarize all what I did, well, we proved that actually that the probability that x n bar belongs to G, that this is larger or equal than mu lambda of Zn bar minus alpha less than delta times this exponential minus lambda minus n lambda alpha plus delta minus m of lambda. And here I'm choosing lambda as m prime minus 1 at alpha. So this means that if I take now a logarithm on the left-hand side and I divide that by n, this is larger or equal than 1 over n log this probability plus but there is a minus sign, so that becomes a minus. I'm dividing by n, so this n will cancel to. So let me rewrite what we had before. So I'm taking the log, so this exponential goes away. Then I'm dividing by n, so this n goes away. And here what I get is minus lambda. And let me write that as lambda alpha minus m of lambda. And then I have a minus delta times lambda. So this is what we proved. We proved that 1 over n log of this probability, it's bounded below by this expression. Now if I take the limit, so you see that this expression does not depend on n anymore, while if I take the limit in n, the first expression, well, since this probability is going to 1, the log it's going to 0, dividing by n, it's going to 0 even faster. So what I get from this inequality is that the limit inf of 1 over n log that the probability of xn bar belongs to g, that this is larger or equal than minus lambda alpha minus m lambda minus delta lambda. But now we have to remember that lambda has been chosen according to this equation, so I can replace that, and the expression in times brackets, it's equal to alpha m prime minus 1 alpha minus m of m prime minus 1 computed alpha. And we proved in the last lecture that this is exactly equal to I of alpha. So what we have here is that with our choice of lambda, which was dictated by the fact that we want this expression to converge to 1, and therefore we had to choose the exact lambda which gives the mean of z equal to alpha, that this is equal to minus I of alpha minus delta times lambda. So what we proved is that the limit inf of 1 over n log of this probability, it's bounded below by minus I of alpha minus delta times lambda. The left-hand side does not depend on delta. This is true for all delta bounded by delta 0, so I can let delta to 0 to get that this expression it's bounded by actually minus I of alpha. So let me rewrite it here. So what we proved is that the limit inf in n of 1 over n, the logarithm that xn bar belongs to g, that this is bounded by minus I of alpha, and this is true for any alpha in G. So I can optimize this bound in alpha in G. So I take a supremum here for all alpha in G, but with the minus sign, this gives me that this is equal to minus the infimum for alpha in G of I of alpha, and this is exactly what I wanted to prove. So we proved in the last lecture an upper bound, and now we obtained the lower bound with the same rate function. So in conclusion, what did we proved? Well, we proved that if you take any, under the assumptions, of course, which I made, which, as I said, not all are important, not all are needed. If you take a set A, and you ask yourself, well, what's the probability that x n bar belongs to A? Of course, this is bounded by the probability that x n bar belongs to the closure of A, and it's bounded below by the probability that x n bar belongs to the interior of A. And now you can deduce from the upper and the lower bound that, let's say, 1 over n log that the probability that x n bar belongs to A, that the limit sup of this quantity, it's bounded below by, of course, we didn't prove that, but what I claim is that with little more effort you can prove this bound, that this is bounded by this probability, and since A it's a closed set, what you would get is that this is bounded by minus inf of alpha in A bar of I of alpha, and well, that this is of course larger or equal than the limit inf of 1 over n log of the probability that x n belongs to A interior, and this is bounded by minus the inf of over alpha in A0 of I of alpha. So that what actually you have, that this expression, which is you're taking the inf of I over the points, the interior points of A, it's bounded by the limit inf of this expression, which is bounded by the limit sup, and the limit sup is bounded by this expression. So you see that the upper and lower bound that you obtained are pretty sharp, since they differ only by the interior and the closure on the left and the right hand side. And with that, so this completes the proof of the lower bound and of what I wanted to say about large deviations of IID random variable. Let me just mention that these same ideas go through to several cases, in particular to Markov process or Markov chain. So the same order, the same type of argument will provide you upper and lower bound for the large deviations of Markov chains instead of IID random variable. So it's very important to understand these ideas because they will apply to much series of different contexts.